Okay, in this video we're going to look at the synthesis and reactivity of conjugated diene systems. Okay, the take-home lesson from the previous videos has been that conjugation is a very highly stabilizing influence. And if you look at alkene forming reactions that we took up in chapter 5, when you do those in a system that can make a conjugated diene, they actually prefer to make the conjugated system. Because remember, Zaitsev's rule said that we get the more stable alkene. Back when we did chapter 5, the only thing affecting alkene stability was the degree of alkyl substitution. Okay, so if we take that if we introduce something, a new variable like conjugation that has an even greater effect on stability, we're going to see that this is the driving force for forming the conjugated systems. Okay, all right, so let's imagine this alcohol right here undergoing an elimination. If we do this dehydration rather, we have a alpha, and then we're going to form the double bond between the alpha and beta carbons, right? Okay, all right, so back in chapter 5, we said you form the most substituted alkene, right? Well, in this case, if we form the more substituted alkene, it's an isolated diene, though, okay? So this is a tetrasubstituted alkene, but it's also an isolated diene. All right, if the elimination goes the other direction, though, it forms a conjugated diene. So the major product of this reaction is going to be the conjugated diene system. Okay, the other eliminations we've looked at, dehydrohalogenation, also prefer to make conjugated systems. The major product in this case would be the conjugated diene here over the isolated diene that you see there. Okay, a type of reaction that we're going to encounter much later in probably the second half of this class is reactions that make this type of compound, which we call alpha beta unsaturated carbonyl compounds. Okay, so elimination reactions in these systems also prefer to form the conjugated system. Both the dehydrohalogenation and the dehydration reaction both form this one, and not this one, because again this is not a conjugated system, right? Because there's an sp3 carbon there between them. The degree of alkyl substitution is the same in both, but it prefers to form the conjugated one. Okay, let's look at some of the unique reactivity that we associate with conjugated diene systems. Okay, if we look at isolated dienes up here, we react this compound with HBr. Nothing special happens. If we add 1 mole, it goes to the more substituted carbon. It gives you the Markovnikov product, as you'd expect. And if you add a second mole, it would just add to the other alkene in exactly the same fashion. Okay? So what we see here is that there's nothing special about an isolated alkene. It's like two independent alkene groups. Everything you learned in chapter 6 can tell you what would be the chemistry of an isolated diene system. Okay, the only concern is, do I add 1 mole or do I add 2, and what's the relative reactivity of the two alkene groups. Okay, if you however add HBr to a conjugated diene, the process is a little bit more complex. All right, so here's, we'll just use this simple diene. This is the simplest conjugated diene of them all, 1,3-butadiene. Okay, if this reacts with HBr, it produces two different products, and we're going to very carefully here add just 1 mole. Okay, and the first product that you get here is totally analogous to the product up here. It's just a Markovnikov addition to one of the alkene groups. But a sizable amount of this product here is also obtained. Okay, so, and let's just look at, we'll call this carbons 1, 2, 3, and 4. All right, the product on the left we're going to call the 1,2 addition product, and the product on the right we're going to call the 1,4 addition product. This is because if the hydrogen's at carbon 1, the bromine is at carbon 4. Okay? The 1,2 addition product is the major product when the reaction is conducted at low temperature, but the 1,4 addition product is the major product when the reaction is conducted at higher temperature. Okay, so if we look at the mechanism here, it starts out the way it did in chapter 6. We're just protonating the alkene group with HBr. Okay? All right, and this is giving us the carbocation. Of course, the carbocation, a resonance structure can be written for the carbocation right here. And if you imagine this resonance form reacting with bromide, and if it reacts where the positive charge is, it would produce this compound here. If this resonance form reacts with the bromide, it would produce the 1,4 addition product here. Okay? All right. So what does this mean? How do we explain this temperature difference? Well, if you look at the relative stabilities, this is a disubstituted alkene, and this is a monosubstituted alkene. So this product here, we'd probably expect it to be more stable or lower in energy, right? Okay. So what happens at higher temperature? An SN1 type reaction is occurring, okay? Above room temperature, these species are in equilibrium. Now, how does this equilibrium happen? All right, so what we do here is we just dissociate the bromide in a classic SN1 reaction. So here, there's an equilibrium between here and the ionic compound here, the carbocation, bromide anion pair. Okay, and when the system's completely at equilibrium, what you're going to see is that the equilibrium ratio favors the relative stability of the products. Remember this important equation here. Okay, so if the system is completely at equilibrium, we would expect more of the product on the right. Frankly, it's actually quite difficult to predict what's going to be the kinetic product and what's going to be the thermodynamic product. In this first class in organic chemistry, all we're really expecting you to do is just to recognize that you can form both the 1,4 and 1,2 addition products and be able to draw them if you saw them on an exam. Okay, if we wanted to explain why we would get more of this, we would probably say that if you compare these two resonance forms, this one over here would probably be more important because it's a secondary allylic carbocation, whereas this one is a primary allylic carbocation. Okay, So if you look at the resonance hybrid and think about where is most of the positive charge, you'd probably say it would probably be concentrated over at this carbon because this is technically a better carbocation, or the carbocation aspects of this resonance structure are better than the carbocation aspects of this. So when bromide attacks, it's going to see more positive charge here than here. But at equilibrium, we just look at what's the relative stability of the products, and if we look at the degree of alkyl substitution, we can see that the 1,4 addition product, being a disubstituted alkene, is of course more stable. Okay, and any of the carbocation and free radical reactions that we encountered in Chapter 6 can undergo both the 1,2 and 1,4 addition pathways with conjugated dyene. So this is a potential reaction for any of those systems. Okay, let's look at it on a potential energy diagram. How do we explain getting the less substituted product preferentially? It has to do with the fact that the energy of activation for forming, this is for forming the 1,2. Energy of activation for forming the 1,2 product is lower than the energy of activation for the transformation of the carbocation into the 1,4 product. So if we look totally at kinetics, remember that this is dependent on the activation energy, we would expect this product here to form faster than this product here because of this difference in reaction activation energy. Okay? All right. And normally, I guess, since this is very reactant-like transition state according to the Hammond postulate, okay, we're really concerned with where is the carbocation, and this, again, like we were saying before, is more likely to be here than over at here, because this is secondary, this is primary. Okay, they're both allylic, so they're both pretty good for that reason, but secondary allylic is better than primary allylic. So in this resonance hybrid, we're just saying there's more partial positive there. Notice how my partial positive sign was bigger on the left side than on the right side. Okay. All right, so let's do a problem here. Again, pause it, do it, and then look at the answers. Restart it and look at the answers. We're going to show the 1,2 and 1,4 addition products from each reaction. The top reaction is kind of messy. There are an awful lot of products here. The bottom, because chlorine is a symmetrical reagent, it allowed chlorine and chlorine. It's a little cleaner. Okay. All right, so both of these double bonds here are disubstituted. This one here is probably more reactive because there's the potential to form a tertiary carbocation from that double bond. Okay. All right, so if we look at all the 1,2 and 1,4 addition products, there's quite a lot of them. Okay, so let's imagine protonating the end. That gives us this one, which has plus there. Okay. All right. So these are our two resonance forms. Okay, and 1,4. All right, the alternate structure comes from protonating the other alkene group. Right, okay, so we can imagine protonating the other alkene group and we get this. Our resonance forms here. Okay, would be these two. Okay, so guess that's our 1,2 addition product from this pathway. And this is our 1,4 product from this other pathway here. Okay? All right, so this is kind of a complicated reaction. Probably these two, you'd probably say these would be the thermodynamic products because they're they're both tri-substituted alkenes. Okay. But it would be kind of hard to predict the kinetic product. I'm going to make a prediction that this would probably be the kinetic based on the fact that I get this excellent tertiary carbocation and probably a lot of the positive charge is concentrated right there. Okay, let's look at this bottom one. Here we have two different alkene groups. One's tri-substituted, one's di-substituted. This one's probably more reactive. So if our 1,2 addition product from adding to that alkene is here, 1,4 addition product from adding to either alkene would be this here, okay, because again, chlorine is adding a chlorine to one and a chlorine to another carbon, so the 1,4 addition products would look the same regardless of which alkene group you attacked first. Okay, this is the other 1,2 addition product from attacking the di-substituted alkene. Okay, again, if we wanted to predict the thermodynamic products, it would be a tough call between here and here because both of these are tri-substituted alkenes. Okay, here's the other important reaction from this that conjugated dienes do, or that's unique to conjugated dienes, and this is an important one. This is called the DielsAlder reaction. In the DielsAlder reaction, we take a diene, and it has to be in the S-cis conformation. You'll see that when we draw the mechanistic arrows in a second, and an alkene. And when an alkene is involved in a DielsAlder reaction, it's going to get another term. It's going to just be called the dienophile, the diene lover. Okay? When we heat these two together, we get a cyclohexene ring. Okay? All right, we call this type of reaction a cycloaddition reaction. What a cycloaddition reaction means is that we're taking two separate molecules, and when these molecules combine, they form a new ring system. There's a ring where no ring previously existed. We call the DielsAlder reaction a 4+2 cycloaddition because if we look at the pi bonds involved, there's 4 here. Sorry, 4 electrons in these two pi bonds and 2 electrons in this pi bond. Okay. If we look at the mechanism, it's just this bond reorganization shown here, this set of 3 arrows. It occurs in one step without any intermediates. This is often referred to as a no mechanism reaction. That's what the early inventors or early discoverers of this reaction called it. I guess probably some of you are saying that's my favorite kind of reaction. Okay, but all it means is that it's just concerted. We've already had some no mechanism reactions. The SN2 reaction is probably a good example of that, right? Okay. In the process here. Note that we have 1, 2, 3 pi bonds in the starting material, only 1 pi bond in the product, and we form 2 new sigma bonds right there. Okay, the net conversion of 2 CC pi bonds into 2 CC sigma bonds is going to be an obviously favorable process. So the DielsAlder reaction is exothermic. Okay, and this is, of course, remember, sigma bonds are stronger than pi bonds. Okay, this type of reaction, we're going to look at the mechanism. Actually, we're going to see that it does have a mechanism. It's called a pericyclic reaction. It occurs because of frontier molecular orbital interactions. Okay, and we're going to discuss the reason for that later. Okay, I've introduced this as your first DielsAlder reaction because it's the simplest one you can possibly write. But this DielsAlder reaction is not a very good one. It's kind of mediocre. In most of the good, successful, high-yielding DielsAlder reactions, you're going to have what we call an electron-rich diene and an electron-poor dienephile. Okay, so let's review, and some of this is not review, some of this is actually learning it for the first time, what makes something electron-rich and electron-poor. Okay, so these groups here, alkyl, OR, and NR2, these are what we call electron donating groups, or EDGs. These make the system more electron rich. If we were imagining taking an alkene and protonating it, that protonation process would occur much faster if we had one of these groups on the alkene. Okay? All right, we've already seen how we've already described why the alkyl is an electron donating group, right? But these other ones here, it's really the fact that you have a lone pair right at the point of attachment. Okay, and we'll see. We'll re-examine that issue quite heavily in Chapter 12. Okay, let's look at electron withdrawing groups. These make the system less electron rich. All of these have some sort of dipole taking the electron density away that way. Okay? Alright, so just look at nitrile here first. So the cyanide is a very good electron withdrawing group, and that's because we have this partial positive right here at carbon. The nitro group, CF3 group, anything with a carbon-oxygen double bond, an X group, and let's see, we'll add one more, the sulfonate group, just to like an tosylate. This group is also considered to be electron withdrawing. Again, we're going to revisit the concept of electron withdrawing groups in Chapter 12. Okay, but if we have these groups on our alkene becomes electron poor. So these will activate the dienophile part. So let's look at some examples of good DielsAlder reactions. All right, so this first one here, we have an electron withdrawing group right here. Electron donating groups here. And this reaction produces this product right here with high yield and high efficiency. This is a good DielsAlder reaction. All right. Another reason that this is a pretty good DielsAlder reaction is that there's not much energy difference between S-cis and S-trans. They both have about the same degree of steric hindrance, okay? All right, so this one equilibrates between S-cis and S-trans, but there's a high population of the S-cis conformation at equilibrium. Remember, we discussed earlier how the S-cis conformation was less stable than S-trans, but here they're approximately equally stable. All right, this one has ester groups, and you'll see this abbreviation frequently. That's what that means. That's a carbonyl group right there. Okay, this reaction is incredibly facile. Cyclopentadiene turns out to be one of the best. Yeah, cyclopentadiene turns out to be one of the best dienes for the DielsAlder reaction, and that's because this one is basically frozen in the S-cis conformation. Okay. Important point to remember is that we don't lose any carbons, so the CH2 group that we had here in the starting material, it's still present. Okay. So you have to account for where is that, and this is forming a bicyclic system, and the CH2 group is what we call basically the bridge. Okay. All right. This is also an alkyne in the DielsAlder reaction. Notice that when you have a triple bond, that triple bond becomes a double bond. Okay, I haven't written all over the place here in this other structure, but you can see it right there. So the degree of bonding in the original dienophile is going to decrease by 1. If you start out with a triple bond, you'll get a double bond there. If you start with a double bond there, you'll get a single bond. Okay? All right, here we have another diene that's also frozen in the S-cis. Okay, this has an aldehyde group on it and a CF3 group. This is how we abbreviate aldehyde groups in organic chemistry. What you should also note in this reaction here is that the alkene is the transalkene. Alright, so the DielsAlder, we say, is a syn addition. You're going to retain the stereochemistry. These groups, they were trans in the starting material, and they're now trans in the product. So this is characteristic of a syn addition, right? We're retaining the stereochemistry we started with. If we start with trans, we're going to get trans in the product. If we start with cis, we're going to get cis. Okay, so here is a case where our dienophile is cis, right? Okay, and this reaction produces, again, the product where the hydrogens are cis and the carbonyl groups are cis. This is an especially favorable one. This is something we're going to talk about in the next chapter, but this system is has something called aromatic stabilization. Okay, so this is actually quite activated. It's frozen in the S-cis. Okay, we can't really make the S-trans geometry here, and it has an oxygen right on the diene, so it's very electron rich as well. Okay, so that's a particularly good diene system right there. Okay, so let's do a problem here. Which reaction is the fastest, and why is that reaction the fastest? Okay, right, and you should think about this, pause it, then see the answers. Turns out that the top reaction is much faster. And what we have to do is think about the fact that both of these conformations depicted are S-trans, and we know that S-trans is not our reacting conformation. We have to get it into S-cis. So what happens if we get each of these dienes into the S-cis conformation? All right, the top one, no problem. It's not any more strained, or the S-cis isn't any more or less stable than the S-cis isomer of 1,3-butadiene. Okay? But the S-cis here has a serious steric problem. Okay? We're unlikely to obtain a very high population of the S-cis conformation in this second system. So the top one is the one that's going to be faster because it's difficult for the diene in the second case to attain the required S-cis geometry. Okay? All right. I guess I have an extra methyl group here. Sorry. All right. Let's look at some other DielsAlder issues. Rank these 4 reactions in terms of their relative rates. And again, pause the video, think about each of them, think about how electronically activated they are, and think about the S-cis versus S-trans issue as you do it. Okay, so I'm going to go through the answers here. Let's look at these. All right, this first one is going to be the fastest one because we have a diene that's frozen in the S-cis, and we have 2 EWGs on our dienephile. Okay? If you look at just the diene part of this second one, it's actually frozen in S-trans, okay? Frozen. It really can't attain the S-cis conformation at all. The product also is a transalkene in a 6-membered ring. And we know from chapter 5 that we really can't have that type of structure, right? The transalkene has to have at least 8 carbons in it to be isolatable. It does have 2 EWGs, but if you can't get the diene in the right conformation, it's never going to go. Okay, let's look at the next one. It's the second fastest because this diene is going to equilibrate between S-cis and S-trans. S-cis is attainable, but it's probably not the major conformation, but it's not excessively hindered or anything like that. Okay, all right, and in the last one, we're going to rank it not quite as fast as the one above it because it's only got 1 electron withdrawing group. It's got an electron donating group here. Okay, so it's not going to be as good as the one above it. All right, so this is number 1, number 4, number 2, and number 3 as far as the relative rates of these 4 reactions. Okay, let's predict the products of these DielsAlder reactions. What's the product of this one right here? Again, this is a problem. You should pause it, then look at the answers. But the product, we'll just draw really long arrows. Involves those 3 arrows. And we make this product. There's also a stereochemistry issue. You could say that you're going to definitely get the one where these 2 hydrogens are cis here, but the stereochemistry here is uncertain. It actually probably fairly predictable, but that's an issue that we're going to save for a more advanced graduate course as far as the stereochemistry goes at that position. All right, so what are the precursor compounds for this product in the DielsAlder reaction? Okay? What you want to think about here is remember that the DielsAlder makes a cyclohexene, so we have to identify the cyclohexene part of this reaction, right? Alright, so we'll just de-emphasize that part right there. Alright, so we have to think about the retro DielsAlder, the reverse of the DielsAlder reaction, and then we just draw those three arrows right there. Notice that the two groups here are trans. Okay, so the two compounds that we need to combine to make this compound are this dinitrile or dicyanide that you see here, and this diene here, known as furan, a molecule that we will revisit in the aromatic theory chapter, which is the next chapter. Okay. Alright, so let's look at now the reasons for why the DielsAlder reactions go, and this has to do with molecular orbitals. First, let's look at the molecular orbital description of the pi bond of ethylene. This is just the pi bond, not the sigma bond. Remember, the double bond is a sigma bond and a pi bond. We are just looking at the pi bond. Okay, the pi bond comes from overlap of a p orbital at each carbon, and each of these p orbitals would have a single electron. So these two here are our atomic orbitals. Okay, these are, in the side here, the molecular orbitals. This is our net stabilization. Okay, so what we see here is that we have a bonding MO. Okay, this is because we're combining like phases, and it's a bonding interaction. Here, this is anti-bonding. And we're going to refer to this type of interaction here as a node or an anti-bonding interaction. This is where unlike phases are being forced to combine, and this is a destabilizing situation. Okay, we only have two orbitals here, but we can also describe them as HOMO, meaning the highest energy occupied molecular orbital. This is the highest energy orbital that has some electrons in it. We'll appreciate this concept when we look at more advanced pi systems. And this one we're going to call the LUMO. This is the lowest energy one that doesn't have any electrons in it. These are when we're looking at the molecular orbital interactions, we really want to focus on the HOMOs and LUMOs. Okay, here's the net result of that that diagram from the previous slide. Okay, we're looking at the pi and the pi star molecular orbitals of ethylene, the ethylene pi bond, and the LUMO and the HOMO. Okay, when we introduce conjugation, the system becomes more complex. Okay, so we can actually now have 4 orbitals involving interactions of the pi bonds in 1,3-butadiene. Okay, so here's 1,3-butadiene, remember, and ethylene. Okay, we can sort of estimate the relative energies of these orbitals right here by looking at the fact that we have 3 bonds, interactions. We have two bonds and 1 node. Okay, let's spell node correctly. Sorry. Here we have a node, a node and a bond, so we have one bond and two nodes. And here we have nothing but nodes. Okay, completely anti-bonding all the way through, and that is our highest energy orbital of all. All right, so this one we're going to call the HOMO now because it's the highest energy orbital that has some electrons in it. And this one here, psi 3, we're going to call the LUMO because it's the lowest energy orbital that doesn't have any electrons in it. Okay? As far as deriving these molecular orbital diagrams, that's not a requirement in this class. You'll be given them, but take a more advanced physical organic chemistry class, and probably deriving the orbitals would be a part of that, of what you would be required to do in that class. Okay. All right. So what we want to do now is focus on how the orbitals in the two different compounds interact, okay? And I'm going to focus on these two interactions right here, okay? Because when we look at these orbitals, we're interacting a filled orbital with an empty orbital, and here's this diagram. All right, so we're looking at the interaction of the LUMO of the dienophile with the HOMO of the diene, which is what you saw there. Remember the N carbons. Here are the N carbons. They have the opposite configuration, and also if you look at the dienophile, both the LUMO, this is the antibonding orbital, has the opposite configuration there. Alright, so you want to interact the filled orbital with the empty orbital, and this is the important interaction right here. Okay? And this is a net stabilizing interaction. The energy of the system becomes lower because this LUMO and this HOMO interacted. All right, we can have the opposite interaction here. Here's a HOMO of the dienophile and the LUMO of the diene. Okay? All right. And here we see just the opposite, but the same net degree of stabilization. Okay? This one, it turns out, is going to be more important for electron-rich diene plus electron-poor dienophile. This is a concept that probably should be discussed in a graduate class, but what happens here is that electron withdrawal lowers the orbital energy, so this one would go down because of electron withdrawing groups, and electron donating groups raises orbital energy, so this one goes up. So these get closer to each other in energy, and you get your strongest MO interactions when the HOMO and LUMO have similar energies. Okay. All right, you may wonder, as long as we can push arrows, we can make rings, right? What about the 2+2 cycloaddition? Turns out that there really are not many examples of this, and they aren't, and successful examples aren't what we call no mechanism reactions. They actually have, in most cases, intermediates. Okay, so if we imagine these same HOMO-LUMO interactions that were really beautiful for the DielsAlder reaction, they're not so beautiful for the 2+2 cycloaddition. We have to interact the HOMO of one with the LUMO of the other. And what you see here is that you can only have one carbon-carbon bond forming. The other one is actually an anti-bonding interaction. So there's no net interaction here. All right? What if we had the HOMO combined with the HOMO? Okay, well, the interactions have the right signs here, or the right symmetries, but look at this orbital diagram. When you have a field interacting with a field, there's no net stabilization from this interaction, because you have to, if you start out with 4 electrons, you got to put 4 electrons in your MO, your molecular orbitals, so you're going to have to throw an equal number in the anti-bonding as you do in the bonding. Okay? Alright, so the 2+2 cycloaddition is going to be a lot harder than the 4+2 cycloaddition. You might be saying, duh, what about ring strain? Well, angle strain. Yeah, that's probably a component of it. It's not going to be as exothermic, but there are lots and lots of examples. There's examples where we have systems that are more complex than butadiene, like if they have 3 double bonds in conjugation, or 4, and some of the cycloaddition trends hold true there. What we call this theory here, won the Nobel Prize back in the early 1970s, is the conservation of orbital symmetry. And we're going to see that there are many reactions like the DielsAlder that are pericyclic, that are governed by these HOMO-LUMO interactions in pi bonds. And we'll see that this trend holds throughout. Okay? Alright, turns out that if you photolize the system, okay, that you can get the electron, one electron to go from the HOMO to the LUMO. This is now going to be called a SOMO, a singly occupied molecular orbital. Now if you do this net interaction, there's some degree of stabilization because there's 2 bonding and 1 anti-bonding, so it's kind of like a half bond there. So if you shine ultraviolet light on the system, there are many successful examples of 2+2 cycloadditions where they're done in the presence of ultraviolet light. And this is because now you can interact these HOMOs in a energetically stabilizing interaction. Okay, so light, UV light, causes 1 electron to go from HOMO to LUMO. Okay. Here's just a summary here. You're probably confused by this. Remember, I said that I would give you the actual diagrams. Here's some of the things I'd like you to know. If you're given a blank molecular orbital diagram, place the correct number of electrons into the correct orbitals. That's the lowest energy ones. Identify the HOMO-LUMO and bond order after doing task 1. And understand why the HOMO-LUMO interactions are better than the HOMO-HOMO or LUMO-LUMO interactions. You should gravitate to the HOMO and LUMO interactions, okay, as to whether the reaction is going to be allowable or not. All right. Turns out the DielsAlder reaction was not the first pericyclic reaction covered in this class. Ozonolysis was the first pericyclic reaction. Okay, so this is not something I would put on the exam, but let's just look at it. This is a type of pericyclic reaction known as the 1,3 dipolar cycloaddition. Okay, so that's involved in our formation of the molozonide. Okay, we can now do a retro version of this reaction, but in a slightly different way. This is the retro 1,3 dipolar cycloaddition. It gives us an aldehyde and a carbonyl ylide. We're just now going to turn the aldehyde upside down along this axis and do the 1,3 dipolar addition the opposite way. And this is how we get the ozonide. Okay, so this is the step here that breaks what was originally the carbon-carbon double bond. This converts it to a single bond, and this retro 1,3 dipolar cycloaddition is what actually breaks it. Okay, we'll later encounter a few other pericyclic reactions in this class. This is in nature, this is probably the most important pericyclic reaction of them all. Sunlight making vitamin D. How does that happen? Well, an enzyme in cholesterol converts cholesterol to dehydrocholesterol, shown here, and then sunlight causes not the DielsAlder reaction, but something called a electrocyclic ring opening, which is also a pericyclic reaction. All right, and this produces this, and another pericyclic reaction occurs called the 1,7 hydrogen shift, making vitamin D. Okay, so you've always heard if you need vitamin D levels, go out in the sun, and this is exactly why it occurs. Sunlight causes these pericyclic reactions to proceed on a cholesterol-derived biomolecule. All right, here are popular molecules that are in commercial sunscreens, and what you can see here is they're halaciously conjugated molecules that will absorb the ultraviolet light given off by the sun. So the idea here is that these molecules that you've slapped on yourself will do the absorbing and not the DNA molecules. Okay, and when, let's see, yeah, 2+2 cycloaddition. This is actually an important event in carcinogenesis. Okay, so it's thought that one of the reasons that sunlight leads to skin cancer is because they cause DNA bases to do 2+2 cycloadditions. Okay, all right. And finally, let's see, we're going to do a problem here, design a multi-step synthesis for this compound. You're going to have to use a Diene file of your choosing as the source of extra carbons. All right, so if you want to look at this molecule here, again, pause it and try it yourself before looking at my answers, okay? There's 2 cyclohexadiene units here, okay? I have a cyclohexadiene unit going, follow the cursor this way, and I have one going this way. All right, this latter one is the one we're going to choose because it has electron withdrawing groups, and that's the one that we can use in the DielsAlder reaction, right? All right, so if we think about what are we going to use, there's our retro DielsAlder reaction. We're going to use cyclohexadiene and this alkene right here. Recognize that they are definitely trans, so they need to be trans in our starting material right here. So they're also trans. And here you should take advantage of the liberal directions. Use any Diene file. Okay. All right. So our challenge is now how to convert cyclohexanol into cyclohexadiene. Okay. That's kind of a going to take several steps. As you see here, it says it takes 4 steps, so it must take 3 steps to do that. All right, let's think about, we know how to turn cyclohexanol into cyclohexene, right? Just dehydrate it. But we need to think about how we get the second group in there. And the best way to do that is by an E2 process. So we're going to treat this bromide here. We're just going to do an E2 on it, okay? So, and that bromide is secondary. It's also allylic, but probably if we use a strong base, that's it's going to do an E2 preferentially. All right. Cyclohexene converts to that compound, of course, just by NBS and light. And that is just our old friend, the dehydration reaction from long ago. Okay, so dehydration followed by introduction of a bromine followed by E2, and then we do the DielsAlder reaction. Will give us this product. The critical aspect of this problem here is probably analyzing the problem and determining what you need in the DielsAlder. Once you figure that out, the rest of it is kind of like the synthesis problems you had done in the past. Okay, let's look at one final thing, and this is polymerization. Okay, so conjugated dienes engage in 1,4 polymerization. Okay, so we're adding our peroxy radical. To make a new radical there. It's got a resonance structure. Okay. And this is going to react with another one. Okay. Okay, and I think we have, where's our double bond here? Okay, and this happens over and over many, many times, and this gets us our polymeric system. Okay, it's critical. This is a very simple diene, 2-methyl-1,3-butadiene, known as isoprene. And this is nature's building block. Okay, if you look at natural rubber, it's actually the polymer of isoprene, but purely of the Z geometry. Okay, if we look at the E isomer, this is another polymer known as gutta percha, and these two compounds here, these two polymers have very different properties. Natural rubber, we're probably associated with its flexibility and various other properties used in tires and rubber gloves and things like that. So it's a very flexible molecule. Gutta percha, however, is a very hard, brittle molecule. It's used to cover golf balls. And so here we see an important example of where stereochemistry really matters. Okay? All right. And we see that depending on how you polymerize this, if you got E or Z, you would have very different materials. Well, it turns out I don't think industry's really ever learned how to polymerize isoprene and get complete rubber or complete gutta percha. You get something in between, but this caused a problem for the U.S. during World War II because all the rubber producing areas of the world were kind of taken over by Japan at the time, and there was a big push to learn how to make artificial rubber. Okay, so it's still an unmet obligation, but it turns out, I guess, you can make a very rubber-like substance from making a polymer from two different compounds, styrene and butadiene, and that makes something very rubber-like. So it's there are artificial rubbers, but they're not usually made from polymerizing isoprene because of this stereochemistry issue. Okay, I think this is it for the diene chapter. The next chapter we're going to add one more double bond into conjugation, and we're going to look at triene systems or aromatic or benzene systems in the next